Welcome to today's deep dive. So, imagine a 6-axis collaborative robot swinging a 50-pound payload at absolute full speed.
Right, which is a massive amount of kinetic energy.
Exactly. And if a single joint's communication lags by even like a fraction of a millisecond, that machine doesn't just stutter. I mean, it becomes a little wrecking ball.
Yeah, a very dangerous one.
So today we are tearing into document EP0056. The mission here is to really decode the invisible physical architecture and the fail-safes that keep these modern precision transmission systems from basically tearing themselves apart.
We really have to start with the physical constraints first. I mean, the document highlights the ISO 9409-1 standard for mechanical interfaces.
Right, which defines mounting specs like the pitch circle diameter.
Yeah, exactly. It's essentially like a modular chassis in motorsport. You know, you can hot swap a powertrain.
Like replacing a planetary reducer with a cycloidal drive.
Yeah, exactly that. And you can do it without having to remachine your entire suspension geometry.
Okay, let's unpack this a bit. Because having modular hardware, like universally standard Lego bricks, doesn't really matter if the timing is completely off.
No, it doesn't. And that's exactly where the real-time field bus comes in, specifically EtherCAT.
Right.
We're talking about incredibly demanding sub-millisecond synchronization across literally every single harmonic actuator on the arm.
But wait, doesn't that extreme synchronization speed create like a massive structural bottleneck?
Oh, absolutely it does. I mean, if you have 6 joints sending position feedback and drawing current every single microsecond, a traditional central processor will just choke on the bandwidth.
It just can't handle it.
Right, and that strict data limit is exactly why the architecture is forced into what we call distributed control.
Okay, here's where it gets really interesting to me. If we shift the control logic, the position loops and the integrated strain gauge data away from the central computer.
And right into the smart drive circuits in every joint, yeah.
Right. But aren't we just multiplying our points of failure? Like, why build 6 fragile mini-computers on a wildly swinging arm instead of keeping one big, robust central unit safe in the base?
Well, the physics basically demand local processing to eliminate latency. The central unit handles the macro path, sure, but the joints, they have to process their own micro-adjustments locally to stay within that unforgiving sub-millisecond window.
Ah, I see.
But, relying on local joint data introduces a completely different spatial problem. The mechanical 0 point of a joint and the electronic encoder's 0 point, well, they rarely align perfectly out of the box.
Which is where the calibration offset comes into play, right?
Yes, exactly.
Because if a technician swaps that cycloidal drive we mentioned earlier, a tiny, like 0.1 degree misalignment at the base joint might seem negligible locally.
Right, but if that offset isn't updated in the non-volatile memory, that tiny error just massively compounds over the length of the arm,
making a huge difference at the end.
Exactly. It translates into a massive physical deviation at the tool center point. So your precision welding robot instantly turns into a major hazard if the digital map doesn't match the new physical reality of the hardware.
Okay, so I've got this perfectly calibrated, distributed system keeping everything sync. But what happens when the physics break down? Like if the robot hits a rigid object and the flex spline is about to shatter.
That's when you rely on safe torque off, or STO. It's the ultimate hardware failsafe.
So what does this all mean in practice? Like, why use STO instead of just hitting the ultimate kill switch and pulling the plug on the main power?
Because if you cut the main power, you drop the entire network. You lose your tracking, your position data, and all your EtherCAT communication.
Oh, wow. I didn't think of that.
Yeah, so STO acts more like a digital clutch. It physically interrupts the pulse width modulation signals flowing to the power semiconductors, but without shutting off the main power.
Ah, so the motor remains powered and actively communicating on the network. But the hardware circuit renders it physically incapable of generating rotational force.
Exactly. That is the brilliance of the mechanism. If the system detects a potential ratcheting event where gears might slip, STO instantly cuts torque to protect that delicate flex spline.
But the nervous system stays completely online.
Right. You isolate the mechanical danger without forcing a massive time-consuming system reboot.
That completely changes how you look at a robotic arm on a manufacturing line. Next time you see one, you aren't just watching metal move.
No, it is a constant invisible negotiation between physical force and digital control.
You're watching this highly orchestrated balance of modular physics, distributed logic, and hardware-level clutches working in sub-millisecond harmony.
Perfectly said.
Which leaves you with a really wild thought to chew on. with control becoming completely distributed and these physical interfaces becoming universally standardized. Are we approaching a threshold where these precision machines will simply diagnose, calibrate, and upgrade their own hardware without human engineers ever needing to step onto the factory floor?
It's definitely where things are heading.
Something for you to keep in mind until our next deep dive.